very excited to introduce to you Dr. Guillermo Gonzalez.
Good morning. Happy to be here and glad you were here, even though it was a rainy morning. So today I would like to talk to you about beauty and scientific knowledge. This has been quite a year with regard to beautiful things, awe-inspiring things. For those of us in the United States, we were treated to a total eclipse of the sun, the first one since 2017. Show of hands, how many of you saw that, the total part of the eclipse? Great. I also witnessed that one. That was my third total eclipse. I can never get enough of those. Hope to be able to see more in my lifetime. And then unexpectedly, the eclipse was very expected. In fact, expected to the point where we could predict the timing of the eclipse to within 1 second of time and the path to within a few meters across the surface of the Earth. Highly predictable. But then we were treated to an unpredicted event about a month later when we had a solar superstorm that created global aurora borealis, or aurora, I should say. Aurora borealis in the north, aurora australis in the south. Both hemispheres saw that. How many of you saw the aurora borealis display? Oh, I don't think anybody in here saw it. Oh. But keep an eye out. That might happen again because we're near sunspot maximum, and that's the kind of things that happen when the sun is very active. You have these display aurora around the Earth. If any of you read any of the blogs or news reports about following the eclipse or the aurora display, you had similar qualities described from both events. People were awe-inspired. They described it as a beautiful thing. And they took great effort, especially to go see the eclipse. Some traveled many, many miles to the path of totality. And they said they were amazed by the phenomenon. And some of these descriptions came from scientists, not just lay people. And then there's a possibility that we may be able to see a very bright comet later this year, assuming it doesn't fall apart or disintegrate, which happens from time to time with comets. So we may not yet be done with awe and wonder this year. So today, I'd like to present, okay, here we go, a new argument, at least new to me, and so I'll argue that there's a connection between beauty and nature and the acquisition of important knowledge about nature. I'll make cumulative case argument based on multiple relatable examples, which I have listed on this slide. As a corollary, I will also argue that Earth exhibits greater beauty and provides more opportunities for scientific discoveries than other places in the cosmos. Now, if you're familiar with the book that Jay Richards and I wrote, The Privileged Planet, this has a little bit of overlap with that, but there's some new material here that we don't cover. In particular, the aspects of beauty and awe and wonder that certain phenomena invoke in us when we witness them and experience them. And so the examples I have here, the starry night sky, rainbows, total solar eclipses, bright comets and meteors, aurora, electrical storms, are all kind of examples of events that many of us have witnessed, or phenomena many of us have witnessed, or many people see them at a sort of regular basis. Some are rare, some are not so rare. How many of you have experience with at least one item on that list? Good. All right. So is the Earth special in regard to displaying these phenomena, or is it typical? And do I dare try to answer even a why question? Why can we see them? Why do we have the privilege of enjoying these phenomena on the earth? So let me just go over some of the more general aspects of these phenomena. Just make some simple observations. So the following things they have in common, I think. They elicit awe, wonder, and surprise in us when we experience them. They're widely visible across different parts of the world and at different times. And I think this one in particular is highly significant. They're gratuitous. We don't need to be able to see or experience these things to exist, right? To exist, we need to gather food, breathe air, oxygen in the air, drink water. That's about it, right? We don't need to see rainbows or the starry night sky or a lightning storm. So you can say in that sense they're gratuitous. And this is the point I really want to make in this presentation today. They lead us to important truths about nature. Now still, these are highly diverse phenomena. They do differ from one to the other considerably. I mean, some are very colorful. Obviously, rainbow is almost the very definition of color. Some are not so colorful. Say, electrical storm. You have the white flashes of lightning. Some are very rare. So aurora displays, depending on where you live on the earth, can be very rare. A total eclipse of the sun is visible somewhere on the surface of the earth every 1.5 years on average. A rainbow, not so rare, especially if you live in a rainy place. The duration varies quite a bit. Night sky you see every night, at least that's clear. Eclipses, again, are moderately rare. Rainbows are pretty common, and they, excuse me, rainbows last on the order of minutes. A total solar eclipse lasts up to 7.5 minutes. The one we just had in April lasted about 4.5 minutes. There are dynamical aspects. Rainbows kind of static. It kind of forms, appears, stays the same, and disappears after a while. Aurora borealis, if you've seen them, are very dynamic. It's like a shimmering curtain of light in the sky. Meteors are very dynamic, very short duration, change from one fraction of a second to the next. And the physical process involved in each of these is very different. And I'll go over some of the physical processes as I go over these examples. So I'm going to start with the starry night sky and start by reading a poem by Walt Whitman, When I Heard the Learned Astronomer. When I heard the learned astronomer, when the proofs, the figures, averaged in columns before me, when I was shown the charts and diagrams to add, divide, and measure them, when I stared at the astronomer where he lectured with much applause. I'm sorry, I have a hard time reading this. Where he lectured with much applause in the lecture room, how soon, unaccountable, I became tired and sick, till rising and gliding out, I wandered off by myself in the mystical, moist night air, and from time to time looked up in perfect silence at the stars. I think many of us who have had the chance to go outside city lights into a dark sky have felt a certain awe when we looked up at the starry night sky on a moonless, clear night. There's just something, I don't know, it's hard to put it in words. That's why I had to quote a poet, because they have a way with words sometimes. Now, there's a more ancient poet who had also put his experience in words. I'm sure you're familiar with this. A Psalm of David. The heavens declare the glory of God, and the firmament showeth his handiwork. Day unto day uttereth speech, and night unto night showeth knowledge. There is no speech nor language where their voice is not heard. Their line has gone out through all the earth, and their words to the end of the world. So David, again, speaking about how the heavens, including the starry night sky, pointed beyond itself to its creator. And here, the word for God in the original Hebrew is El, was a general name for God in the ancient Near East. So God is a creator. So he's somehow, the stars are pointing back to their origin, their source. And they're also a source of information, a source of knowledge. And that knowledge is universal, goes throughout the whole world, and it's continuous. Now, the biblical writers were not the only ones who said that the heavens somehow pointed back to a divine source. Even pagans felt the same way. This is Aristotle, quoted by the Roman orator Cicero. And he, sorry for the length of the quote. I'll go ahead and read it for you. Suppose we were men who had lived always underground in good and well-lighted dwellings, adorned with statues and pictures, and furnished with everything in which those who are thought happy abound. Suppose, however, that they had never gone above ground, but had learned to report and hearsay that there is a divine authority and power. Suppose that then, at some time, the jaws of the earth opened, and they were able to escape and make their way from those hidden dwellings into those regions which we inhabit. When they suddenly saw earth and seas and sky, when they learned the grandeur of clouds and the power of winds, when they saw the sun and learned his grandeur and beauty and the power shown in his filling the sky with light and making day, when again night darkened the lands and they saw the whole sky picked out and adorned with stars, and the varying lights of the moon as it waxes and wanes, and the risings and settings of all those bodies, and their courses settled and immutable to all eternity, when they saw those things, most certainly they would have judged both that there are gods and those great works are the works of gods. So again, even people who were not biblical had similar kind of impression to what David wrote about, and also Paul in Romans 1:20. They pointed to the grandeur and order of nature as evidence that it was created by God or gods. Summarizing what the starry night sky reveals, and a lot of this is captured in Psalm 19:1, has orderly motions. It's universally accessible to everybody around the world, not just to a few. It's continuous, day after day, night after night. There is limitless depth, and I'll have a few words to say that in a little bit, so I'm not going to say much there. It's colorful. Have you noticed that the stars come in different colors? Some are red, many are blue, some are yellow. It's gratuitous again. Right? Who ordered that? Why can we see the stars? We don't need to see the stars to live. It's completely gratuitous. It's one of the greatest mysteries, in my opinion. Why can we see the stars? And it's got a certain grandeur and beauty to it. And some of it is inexpressible, although some poets have tried to express it in words. So why can we see the stars so clearly? There's a great depth of information, and unfortunately I had this animated earlier, but there was a wide-angle shot and then a zoom in here of these nebulae. It's called the Lagoon Nebula and the Trifid Nebula. You can actually see this with your naked eyes, a little fuzzy patch. And in the night sky, you can see about 3,000 stars on a clear and moonless night. Why so much information? And this picture was just taken with a very small telescope. It doesn't take much effort to go much deeper and see many, many more stars in much more detail. Here's a picture of the Orion Nebula taken also with a small telescope. Beautiful nebulae. And you keep going deeper and deeper. We keep building bigger telescopes. And not just the ones in space, but bigger ground-based telescopes. We have not exhausted the information in the night sky, as evidenced by all the money we spend with the giant observatories. Just an enormous amount of depth to it. It's like seeing a painting, right? But you look at the painting with a magnifying lens and you see more detail. And you look at it with a microscope, you see more detail. And you keep going. It never ends. That's like the night sky. That's what the night sky is. So there's much more information in the starry realm than we can see with the naked eye. And you know, with the naked eye, we can see a lot. We can see there are 5 naked eye planets. And, you know, like I said, thousands of stars are nebulae. There's the occasional visitor to the night sky, comets, which I'll talk about in a few minutes. So our intuition is telling us this is a strange and wondrous situation. So we have gained vast knowledge about the universe. As an astronomer, I can tell you all the information we've gotten by studying the night sky, the stars, learn about the Milky Way galaxy in which we live, about other galaxies, and about cosmology, the study of the whole cosmos as a whole, and discovered by studying basically the night sky that the universe had a beginning. So all this is really totally unexpected, and it's surprising, I would say. This is a quote by the German historian Hans Blumenberg. I think he captures this mystery in a nice poetic way. The combined circumstance that we live on Earth and are able to see the stars, that the conditions necessary for life do not exclude those necessary for vision, and vice versa, is a remarkably improbable one. This is because the medium in which we live is, on the one hand, just thick enough to enable us to breathe and to prevent us from being burned up by cosmic rays, while on the other hand, it is not so opaque as to absorb entirely the light of the stars and block any view of the universe. What a fragile balance between the indispensable and the sublime. Indispensable meaning we have to be able to breathe the oxygen, but the sublime being able to see the stars, even though we don't need it. Now, what about when it's not clear? When it's partly cloudy? Is there anything interesting to see then? Yes, there is. The rainbow. Again, I'd like to start this with by reading a poem. William Wordsworth wrote, "My heart leaps up. My heart leaps up when I behold a rainbow in the sky. So was it when my life began. So it is now I am a man. So be it when I shall grow old, or let me die. The child is father of the man, and I could wish my days to be bound each by natural piety." So just reveling in the joy, the beauty that he sees when he looks up and sees a rainbow. So now we know what rainbows are physically, how they're formed, but for many, many centuries, millennia, people didn't know how they were formed. I mean, they had no idea, but it was intriguing. And I think it attracted many people, smart people, to try to understand them, because it's something that elicits in them a kind of a wonder, a strong reaction. So what do you need? You need directional sunlight, now we know, of course. And the sun has to be relatively low. You need suspended water droplets in the atmosphere, usually after a storm has passed through. And so you need a partly clouded atmosphere with a water cycle. That's what you need. What places on Earth can see rainbows? Well, not every place on Earth produces rainbows. They are, not surprisingly, absent in deserts, unless you get the occasional thunderstorm that passes through. But generally, you're not going to see very much in the desert, like the Sahara Desert especially. The Arctic regions, you're not going to see rainbows. So Antarctica is out, so is Greenland. The places that are most likely to produce rainbows are near the equator, places where there's a lot of rain, not surprisingly. Also islands. Islands are very good for rainbows, like Hawaii. So it tends to correlate with human population, the visibility of rainbows. So where are rainbows not visible? Well, if you want to be most general, where are they not visible in the solar system, right? What about the moon and Mercury? Well, they don't have atmospheres, so they don't produce rainbows. And Mars also is too dry. What about the surface of Venus? It's got clouds. Problem is it has too many clouds, right? So you don't have direct sunlight reaching the surface. So Venusians don't get to enjoy rainbows if they existed. So really, the Earth is the best place in the solar system. You have the giant planets, but they don't really have solid surfaces, is a problem. So the Earth really does seem to be privileged in producing rainbows. We talk a little bit about the science of rainbows. I like to think of a rainbow as a giant clue writ large across the sky. A clue to what? Well, the invention of the most important tool of the astronomer, and also important tool of the chemist, the spectroscope. Newton and other contemporary scientists experimented trying to reproduce the rainbow artificially. They passed sunlight through glass prisms and were able to make an artificial rainbow. Now we call that a spectrum. And then in the 19th century, chemists did experiments by taking a pure element or some simple compound, putting it in a Bunsen burner flame, heating it up, causing it to emit light, and they pass that light through their prism and looked at the spectrum, and they found that each element has a unique spectral signature or fingerprint. So we can identify different elements if they're heated up, and then we look at their spectra. And astronomers began to look at the spectra of the spectrum of the sun. And when they looked at it in high detail, they found that it wasn't just a continuous spectrum like you see in a rainbow, but when you look at it really closely, it's interspersed by many dark lines. And originally those were called Fraunhofer lines, named after the German scientists who first observed them. But then the astronomers began talking to the chemists who had been doing laboratory experiments. And for example, in this experiment shown here, you might be able to see on the screen there, there's a thin green line. The chemist has put salt water in this wick, and the wick is then put in the flame. And so what he's seeing is the emission line from sodium atoms from the salt. And when you compare what's called the wavelength or the precise color of the spectral line that the chemist produces in his laboratory to some of the Fraunhofer lines, you see that there's a match. And so that way, by comparing the different spectral signatures from the laboratory to the solar spectrum, astronomers are able to identify different chemical elements in the spectrum of the sun. And so we're able to figure out what the sun is made out of by looking at its spectrum at high resolution. And then they attach their spectroscopes to bigger telescopes, and they're able to take spectra of distant stars. And so astronomers are able to figure out the composition and temperature and other properties of distant stars by looking at their spectra. They also measure an effect called the Doppler effect with spectra. And the Doppler effect is an effect you get in a change in the wavelength or the color of the spectrum as an object's moving away from us or towards us. If it's moving away, it's red shifted. If it's moving towards us, it's blue shifted. And that eventually led to the discovery that our universe is dynamic and expanding with the measurement of the first galaxy Doppler shifts just over 100 years ago by Vester Slipher. And that was, again, done with a spectroscope. And that eventually led to the discovery that the universe had a beginning. Now let's move on to solar eclipses. This is a picture of a total solar eclipse I went and saw in India in 1995. That was my first total eclipse. And it wasn't enough for me. I've seen 2 more since then, and that's still not enough. I want to see some more. More, please. Right? And there's people who call themselves eclipse chasers. And they try to fit as many solar eclipses in one lifetime as possible and go see eclipses around the world. I'm not like that. I kind of wait till they come to me, mostly. So the last 2 I saw were in the States. But people who go see eclipses, no matter their age, whether it's a 5-year-old child or an 85-year-old man, looking up at the eclipse sun will both be in awe and feel inspired, and just there's something about it that's an unspeakable aspect to it. It has a strong response from us. Poets have written about them, and various writers. Just to remind you what a total eclipse is, it happens when the moon passes between the earth and the sun. Excuse me. In this diagram, the very sharp or small part of the shadow called the umbra is where the total solar eclipse is visible. If you're underneath that dark part of the shadow, then you can see the total eclipse. If you're under that larger penumbra, then you can only see a partial eclipse. And the 2 are completely different. They're 2 completely different phenomena to experience. If you've seen a partial eclipse, you ain't seen a total eclipse. There's nothing, it's not an approximation to a total eclipse. It's not a total eclipse. It's just a whole set of phenomena associated with total eclipse. But it's amazing about our eclipses. What's amazing is that the angular size of the moon and the sun in the sky almost perfectly match. Right? So why is that? I'm not going to discuss that today. If you want to find out, you need to read The Privileged Planet. But I'm going to discuss the scientific aspects of total eclipses. What have we learned by looking at total eclipses of the sun? So first of all, we can see the sun's corona during a total eclipse. It's the outermost atmosphere of the sun, and extends out multiple degrees away from the sun. You cannot see it any other time. You can also see the chromosphere, which is a much thinner layer of the sun's atmosphere immediately outside the dark limb of the moon that's covering the sun. So it's immediately above the photosphere. And historically, I should say there's also a flash spectrum. If you take a prism, again, going back to the prism, if you take a prism and put it in front of the sun during a total eclipse, you'll see the sun spectrum converting itself from a continuous spectrum into an emission line spectrum. And that's because the bright photosphere of the sun with its continuous spectrum with some dark lines is blocked by the moon. And then all you see is the light from this chromosphere, a thin layer against the blackness of space. It's low density gas, like the element in a Bunsen burner flame in the chemist's laboratory, producing an emission line spectrum of the elements. So the chromosphere produces an emission line spectrum. And you can see it converting from one to the other as the moon covers the last bit of the sun's photosphere and then is in total eclipse. And we can see different chemical elements. In fact, the element helium was discovered during a total eclipse in 1868. The second most abundant element in the universe. So, how else have they been useful to science? Well, we've learned how the spectra of distant stars are produced by looking at the spectrum of the sun during a total eclipse, because after all, distant stars are other versions of our sun. Isaac Newton produces 3 laws of motion. He also published his law of gravity, famously. And what's less known is that Newton's laws of motion and his law of gravity was used to predict the circumstances of the 1715 eclipse over London by several of Newton's followers. And the predictions were accurate to within 4 minutes of time, so vindicating Newton's theories. And then you may have heard of this one more recently. In 1919, Arthur Eddington, British astronomer, set out to test Einstein's predictions with his new theory of general relativity by observing the sun and the stars around the sun that appear in the middle of the day during a total eclipse in 1919 and measured the positions of the stars very precisely. Einstein had predicted that the positions of the stars should be shifted just a little bit because of the sun's gravity. The path of the starlight near the sun on the sky on its way to the earth would be bent a little bit, and so that would cause the positions of the stars to be shifted just a little bit on the sky, and he found Einstein to be correct. That was a very controversial theory at the time, general relativity. And this experiment was the first prediction he made from it, and it passed the test. And so many scientists accepted general relativity following that. And it's been tested at many other eclipses since then, of course, and it's passed the tests. So eclipses have helped us learn about gravity. Another phenomenon has helped us learn about gravity, and that's comets. Here's a picture of Hale-Bopp. Anybody saw Hale-Bopp in 1997? Okay. One or two, yeah. I saw it from downtown Seattle, Washington. That's saying something, right? Seattle is a very bright city, brightly lit. If you can see something in the sky from downtown Seattle, it must be really bright. This was probably the brightest comet in the last 300 years. Every now and then we have a bright comet visiting our skies. And we've learned a few things from comets. First of all, they have these long tails, sometimes stretching halfway across the sky if they're really close, come really close to us. How do those tails form? They form because there's something called the solar wind. There's radiation pressure, light pressure, but particle radiation from the sun as well that pushes the tails back. And we wouldn't know about that solar wind if it wasn't for comet tails, at least as early as we did, before spacecraft. We already knew that there was something called a solar wind because of comets. But comets have taught us a few more things. So you've heard probably of Edmund Halley, the famous British astronomer. He's got a comet named after him. And what's important about Halley's comet? Well, it comes around once every 76 years or so on average. It's kind of famous also because it's about equal to the average length of a human lifespan, 76 years. So if you're born at just the right time and live a long life, you can see it twice in your lifetime. I one time manned a telescope in Arizona, University of Arizona, in 1995-96 during the apparition of Halley's Comet. And I had some people come over to look through the telescope at the comet, and some of them were quite elderly, and they said they saw it at its previous apparition in 1910. That was pretty neat. But Halley famously said, well, there's this observations of a particular comet that looks like it's periodic. It looks like it might be the same comet just coming around every 76 years. So he used Newton's law of gravity and laws of motion to predict the next apparition of this comet, which was in 1758. He didn't live to see that, unfortunately, but he was correct. His prediction came to pass. So that was another very early confirmation of Newton's laws, which is very, very important. Okay. On to the next one. Meteors. How many of you seen meteors? Okay. Those are kind of fun to watch. They last like a second or a fraction of a second. And so they're unexpected. You see a flash of light in the sky. They're kind of fun. But we've learned a few things from them too. They're related to comets and asteroids. We know that now that there are meteor showers that occur at the same time every year. That's because we're intersecting the orbit of a comet that's lost particles on its orbit. Also, many meteors that we see come from the asteroid belt, fragments of the asteroids. And now, if there were no atmosphere, would you see meteors? No. If we had an atmosphere, but it was like Venus, would you see meteors? No. Right? So you have to have the right kind of atmosphere, clear atmosphere, to see meteors. What's cool about meteors is that you can reconstruct their paths. So if you have cameras set up in different locations and triangulate, and they do this a lot these days, you can reconstruct the path of the meteor, and before it came into the atmosphere, it was called a meteoroid, and you can figure out where it came from. So where did it come from? The asteroid belt? Well, you can figure that out. And you go the other direction. Figure out where it's going. And so a number of these bright meteors have led to fragments that have been collected on the ground because we are able to deduce where the path of that streak we see on the sky would leave fragments if it survived. And so a number of fragments have been picked up, and these are extremely valuable to science because some of these samples from the asteroid belt are pristine. They're samples from small objects, small asteroids that have not had geological processing. And so these are fragments from the earliest history of the solar system preserved without any alteration, unlike the Earth, where everything has been altered over the history of the Earth on the surface. Aurora are also quite beautiful to watch. They're very colorful. There's greens and reds. So where are they visible? Well, you probably know that you have to be at high northern latitudes or high southern latitudes to be able to see the aurora. And these are just calculations showing where auroras of different strengths, when there are storms of different strengths, where you can see them. So for really strong storms, you can see them where that red line is. If it's typical intensity of solar storms, it's more like the blue curve. So Canadians get to see them a lot, or people way up in Minnesota or northern Michigan. But it's only occasionally that you get to see them farther south. Like, here in the DC area. Similarly, in Europe, Northern Europeans get to see them more often. So they're mostly a phenomenon of high northern or southern latitudes. And to see them in the Caribbean is very rare. That happened in May of this year. So how do aurora form? Aurora form when you have interactions between particles from the sun, from the solar wind, buffeting the Earth's magnetosphere. And what happens is the particles end up getting funneled near the magnetic North Pole and magnetic South Pole, and you form these aurora ovals. That's what the green little halo is in this diagram, the green halos. And so the magnetic field has the effect of accelerating the particles, but also funneling them. So they're concentrated. And so the aurorae are nice and bright in these northern, high northern or high southern latitudes. So it has to do with the Earth's magnetic field interacting with the particles from the sun from solar storms. Now, if you look at a picture of an aurora like the background to this slide, you say, oh, that's kind of sort of superficially like a rainbow. We have a smooth transition from one color to the other. It's a completely different phenomenon. If you took the spectrum of a rainbow, as shown here, you get a nice continuous transition of colors. Roy G. Biv, right? Red, orange, yellow, green, indigo, blue, violet. I didn't say that in order. Blue, indigo, violet. Now, if you take a spectrum of an aurora, you see emission lines. And the reason there's different colors in different parts of the sky is because certain of those emission lines are produced only in the low density gas regions of the atmosphere, and other emission lines are produced in somewhat higher density regions of the atmosphere. So the red ones tend to be produced at low density parts upper higher in the atmosphere, whereas the green lines tend to be produced more in slightly denser regions of the atmosphere. And so that's why you get the separation of colors. But we've learned a lot about low-density heated gases by studying aurora, like the chromosphere of the sun. You know, the flash spectrum, remember that? The chromosphere of the sun is a low-density region of the sun with heated gas that produces emission lines, sort of like the aurora. And also in space, when we look in space and see nebulae, like the Orion Nebula, they produce emission lines. And some of those emission lines are like the auroral emission lines, including some of the very same transitions from oxygen, like the red line at 6,300 angstroms. So we've learned about nebulae by studying Earth's aurora. What about the other planets? Where else can we see aurora? Well, all 4 giant planets display aurora. We have pictures from spacecraft and from the Hubble Space Telescope. This is a picture of Saturn with the auroral oval superimposed, taken in the ultraviolet, and same for Jupiter. Picture of Hubble, visible image, superimposed with an ultraviolet image, but they don't produce visible light aurora. They produce in the ultraviolet or the infrared. So you would not see aurora if you were on the giant planets, even if you had a clear platform on the planet to see them. There's a recent discovery that the Galilean moons themselves have very weak aurora also, because some of the moons have very weak magnetic fields like Ganymede, and so we can see some very weak auroral emission, but again, if you're on those moons, you wouldn't see the aurorae. They're too weak. So, the Earth is the best place in the solar system to see aurora. Lightning. Lightning occurs when strong winds within thunderclouds make ice crystals and water droplets bump into each other, having sort of friction. Now, you're familiar with static electricity being produced by friction, right? Like when you shuffle your feet on the carpet in a dry day in a room, and you touch the doorknob, you get a spark. Similar kind of thing in clouds. So it creates an electrical charge where the ice and water particles move to opposite sides of the clouds. Over time, the electrical charge builds up. When it becomes strong enough to break through the insulating air, the electrons are released, creating the first spark of lightning. These electrons continue to move rapidly through the air, creating a lightning bolt that travels at an incredibly high speed. Where can you see lightning? Okay, this is data collected from space of lightning flashes between 1995 and 2020, showing you the distribution of lightning across the Earth. Now, not surprisingly, strongest near the equator, right, where thunderstorms are most common. Very rare in polar regions, so you don't get to see them in polar regions. Very rare in desert regions. US gets to see a number of thunderstorms. It's pretty active here, so Central Africa and so on. Now, the land masses get most of the lightning. That's interesting. Not very much over the oceans. Where you do get lightning over the oceans, it tends to be near the land masses. So again, where lightning is visible tends to follow the population. So lightning is awe-inspiring, right? When you're outside and seeing an electrical storm. And of course, that inspired people like Ben Franklin to do experiments, famously tying a key to the end of the string tied to a kite during a storm, and then the string onto what's called a Leyden jar, which is an early form of a capacitor to store charge. And so he concluded that this electric fluid, as he called it, now we call it electric current, was a giant version of a spark like you get in electrostatics experiments. Now, electrostatics is the study of charges that build up on bodies that are charged by usually frictional forces, like rubbing wool with amber, like I said, or shuffling your feet on a carpet on a dry day, or combing your hair on a dry day. All those are examples of electrostatics. They were the precursor to the study of electricity and magnetism in the 19th century. Okay, and with people associated like Faraday and Maxwell, who developed electromagnetic theory and eventually led to modern technology. Right? The most important invention of the 19th century was the electric dynamo, the electric generator, and the electric motor. They're basically the same thing. One is the reverse of the other. Electric motor, electric generator. And so I like to think of the study of lightning as kind of a hint of the power awaiting us if we can corral that power and control it, which we enjoy today, of course, with all these electrical devices and such. What about lightning on other planets? There's lightning that has been observed on some of the other planets. Here's a picture of lightning on Jupiter, made by the Juno probe. They tend to occur in the polar regions of Jupiter, and we think it likely forms in the same way as the Earth, involving water. There is some indirect evidence for lightning in Venus's clouds, though not very much. And could you see it? No. Atmosphere of Venus is extremely thick, and the lightning does not occur in the lower part of the atmosphere. It occurs in the clouds, the very thick clouds. Indirect evidence of lightning on Mars, probably from dust storms. Mars does have dust storms, but they are weaker than the lightning we get on Earth, and so they're probably not visible, or not very often. So I think the Earth, again, is the best place in the solar system to view lightning. So let me summarize those examples that I've discussed. And they're ordered, in my opinion, in order of decreasing importance for science. So I started with what I think are the most important of these phenomena for science, working my way down. That's somewhat subjective. Of course, I'm an astronomer, so I put the starry night sky first. And we've learned all about planets, stars, galaxies, cosmology, that the universe had a beginning. Solar eclipses, we learned about gravity, about theories of gravity, learned about the sun's atmosphere and how its spectrum is produced, and therefore how the spectra of distant stars are produced. We discovered the second most abundant element in the universe during a solar eclipse. Rainbows taught us that spectroscopy is a very powerful tool to learn about the universe around us, and both astronomy and in chemistry. Comets and meteors, again, told us about gravity theory. We learned about the solar wind. We're able to get samples from the asteroid belt, pristine samples from the early history of the solar system. From aurorae, we have learned about how these emission lines are produced in low-density heated regions in nebulae. We learn about Sun-Earth magnetic field interactions. And lightning, learned a bit about electrostatics. And it's the promise of harnessing great energy. Also, it gave us that promise. Now, in each of these, people were attracted to these phenomena because of their beauty, how awe-inspiring they are. It inspired people to want to investigate and learn. It's like, I always think of a rainbow, somebody saying, hey, look, stupid, there's something important here I want you to learn about. Pay attention. Now, let me talk a little bit about just the beauty of the Earth in terms of its color. I think color has there's a beauty of, aspect of beauty has to do with color. There's a famous space artist named Don Davis, and he's got a website here from 2002. He's done a lot of great space art over the years. He illustrated one of the articles I wrote once in Scientific American. Anyway, he made this palette, this color palette, for the different planets, tried to be as accurate as possible using pictures from various spacecraft, from various missions to the planets. And it's interesting that the Earth has the most diverse color palette in the solar system of colors. So it's got greens and blues and browns and tans and white. Larger color palette than the other planets. So I want to end just by reading a poem, kind of tying all this together. Beneath the cosmic vault, celestial dances unfold, where science and wonder intertwine a tale untold. In eclipse's twilight, we stand in silent awe, as moon and sun align, revealing nature's law. Stars, ancient sentinels, keep watch throughout the night, their distant fires kindled an endless fount of light. We map their constellations, probe cosmic mysteries. Each answer sparks within us deeper reveries. A rainbow's arch, a spectrum born of sun and rain, reflects the light of knowledge and refracted through our brain. We parse its prismic secrets, yet marvel at its grace. A bridge of understanding spans both time and space. Aurora's ghostly glow ignites a strange delight as particles conspire to paint the polar night. We probe the magnetosphere, discover how it gleams, yet still the sight entrances, a portal into dreams. A comet streaks the sky, a fleeting icy dart, its tail a ghostly plume, a celestial work of art. We trace its ancient path, unravel cosmic history, while watching as it fades into enduring mystery. In storm's electric heart, the lightning's jagged blade reveals a fearsome beauty, raw power on parade. We chart its forked trajectories, learn how it forms, yet thrill to hear the thunder in nature's raging storms. In this grand classroom, the lessons never cease. Each answer leads to questions, a cycle of release. We learn, we grow, we marvel, curiosity aflame, as nature's prompting guides us through this endless game. These wonders woven together like cosmic dreams hint at a grander design, a truth that softly gleams. For in creation's intricate unfolding scheme, we sense a deeper meaning, a universal theme. These marvels point us toward a well of inspiration, a source of awe and beauty, a font of revelation. In dance of stars and planets, in play of light and sound, a cosmic symphony awaits, a truth yet to be found. So let us wander awestruck through nature's grand museum, where science is our guide and wonder our Te Deum. For in this temple of creation, this universal show, we learn, we grow, we marvel, our spirits in reverence grow. Thank you.